In this lesson, I'm going to talk to you about raising a binomial to an exponent. You have learned that the expression x plus y to the second power can be expanded and written as x squared plus 2xy plus y squared. You also know enough about the distributive property to prove that x plus y to the third power is x cubed plus 3x squared y plus 3xy squared plus y cubed. In this lesson, you will discover how these expansions relate to permutations. Number 1. Start with the expression x plus y to the second power. When you expand the expression without using exponents or combining like terms, the expansion follows the steps below. Fill in the blank. X plus y to the second power is x plus y times x plus y, and when you multiply these binomials, multiplying the first by the first, and then the outer terms and the inner terms and the last terms, you get this right here. X times x is xx. X times y is xy. Y times x is yx. And finally, y times y is yy. It is common to write xy plus yx as 2xy. If you put these two terms in alphabetical order, this can be written as xy. So you have xy plus xy, which is two of them, 2xy. Before you combine the terms, though, you can see that there are two ways to write the term xy. You can write xy or yx. There are two ways to arrange two letters. Number 2, suppose you have three letters, A, B, C. How many ways can you arrange three letters? Write all of the arrangements you can find. I can first write them in the order I see them, A, B, C. I could switch the order of B and C to write A, C, B, and then I can pick a different first letter. I can start with B and then write B, A, C, or I can switch A and C to write B, C, A. Finally, I can start with the letter C and write C, A, B, or I can switch B and A and write C, B, A. There are 6 ways you can arrange 3 letters. Number 3, how many ways can you arrange 3 letters if there are 2 x's and 1 y? For example, one option is xxy. Write down all of the arrangements you can find. Here's the first option of xxy. To get another arrangement, we can switch the ordering of this x and y. We can write the first x as it is, and then put y next, and then x again, x, y, x. We can move this y to the beginning to create another arrangement. That would give us y, x, x, and that's the only 3 options we have. We have one letter that is y, and the other 2 are x's. That y can either go in the third spot, or the second spot, or in the first spot. So we have 3 possible arrangements if there are 2 x's and 1 y. Number 4. Suppose you have a coin with an x on one side and a y on the other side. If you flip the xy coin 3 times, how many possible outcomes are there? Write down all of them. One option is that you might flip the coin and the coin will land on x all 3 times. That's the only option that has 3 x's. Let's look at the options that involve 2 x's. You could start with 2 x's and then flip a y, or you could have the first and third be x's and the middle one is a y. And finally, you could start with a y and then have 2 x's. You could also get 2 y's. Suppose you started with 2 y's and then had an x. You could also have the first and the third be a y and the middle an x. Or you could start with an x and then follow that with 2 y's. And finally, you could flip the coin 3 times and get y all 3 times. There are 8 total possible outcomes. Another way to see that is to imagine flipping the coin 3 times, and then to think about how many options are there for each flip. The first time you flip the coin, there are 2 options, and then there are 2 options for the second flip and 2 options for the third flip. When you multiply those together, you get 2 times 2 times 2, which is 8. Number 5. Expand the expression x plus y to the third power. The work is started below. Continue the expansion, but do not use exponents or combine like terms. X plus y to the third power can be written as x plus y multiplied by x plus y squared. And x plus y squared, we saw earlier, is xx plus xy plus yx plus yy. If we multiply these 4 terms by the binomial x plus y, we can distribute both of these to these 4 terms. X can be multiplied by each of these 4, and y can be multiplied by each of these 4. I'll take one at a time. Let's first look at the x. If I multiply x by xx, I get x, 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 3 x's. X multiplied by xy is xxy. X multiplied by yx is xyx. And finally, x multiplied by yy is xyy. Now let's multiply the y term. Y times xx is yxx. I'll put that on the next line. Y times xy is yxy. Then we have yx. And finally, y. When you expand this expression, there are 4 terms here in blue that start with an x, and 4 terms in red that start with a y. There are a total of 8 terms. Number 6. In the previous scenario, count the number of terms that contain 2 x's and 1 y. When you add them together, how many x squared y terms are there? I will underline each of the terms. This term has 2 x's and 1 y, as does this one and this one here. There are 3 terms that have 2 x's and 1 y. They would each be x squared y if we used exponents to simplify the way we write those terms. Number 7. In the expansion of x plus y to the third power, why is the number of x squared y terms the same as the number of x y squared terms? We see that there are 3 terms that are x squared y. An x y squared term would have 2 y's. There's 1, 2, 3 terms that have 2 y's. To see why that is, I'll start with 3 blanks. Every term in this expansion has 3 letters. If I want to place those 3 letters, then I have 3 spaces to choose from, and if I look at this term has 2 x's in it. The number of ways that I can choose 2 x's, if I have 3 to choose from, is 3 choose 2, the combination of 3 choose 2. When I'm choosing 2 x's, I can also look at that another way. I can say that I have 3 blanks, and I really want to know how many ways can I choose to just have 1 y. I can put 1 y in the first spot, or the second spot, or the third spot. There are 3 ways to place that 1 y. 3 letters to choose from, and I want to choose 1 y. So 3c2 and 3c1 are both equal if we just look at the 2 ways to think about x squared y. You can look at this term as picking 2 x's from 3 possible letters, or picking 1 y and putting it in 3 possible places. If you want to make an xy squared term, it's the same concept. You can either think about it as having 3 letters to place, and you want to choose 2 y's, or you have 3 letters to place, and you want to choose 1 x. We can see up here that there are 3 x squared y terms, and there are 3 x y squared terms. Number 8. Look at the previous scenario another way. Suppose you have 2 knives and 1 fork. Part A. In how many distinct ways can you arrange 2 knives and 1 fork? If I use the letter K and F, I could put 2 knives first, and then I could place a fork, or I could put the fork in the second position, or I could put the fork first. There are 3 ways I can arrange 2 knives and 1 fork. I have 3 pieces of silverware to place, and I want to place 2 knives, or I could think about it as having 3 pieces of silverware to place, and I want to place 1 fork. Either way, it is the same, and it is equal to 3. Part B. In how many distinct ways can you arrange 1 knife and 2 forks? If I again use K and F, I can put the knife first, and then 2 forks, or I can put a fork first and the knife in the middle, and then another fork, and finally I can place the 2 forks first and put the knife third. There are 3 distinct ways that you can arrange 1 knife and 2 forks. Number 9. Suppose you flip the previously mentioned XY coin 4 times and write down the 4-letter sequence. Part A. How many possible 4-letter sequences are there? You are flipping the coin 4 times. Each time there are 2 possible ways the coin can land. It will land on X or it will land on Y. So every single time there are 2 options. If I multiply those together, I get 2 to the 4th power, which is 16. There are 16 possible 4-letter sequences. Part B. How many of the 4-letter sequences have 3 X's? The sequence contains 4 letters, and of those 4 letters, I want 3 X's. So I need to choose 3. One way to calculate 4c3 is to write it as 4 factorial divided by the difference between 4 and 3 factorial multiplied by 3 factorial. If I simplify the bottom, 4 minus 3 is just 1. So I have 1 factorial, which is just 1, over 3 factorial. And I can simplify this when I realize that the top is 4 factorial, and that's 4 times 3 times 2 times 1, or 3 factorial. And in the denominator, there's a 1 and a 3 factorial. Those 3 factorials make a disguised form of 1, so I'm left with 4 divided by 1, which is just 4. There are 4 sequences that have 3 x's. You can also realize that there are only 4 ways you could create this sequence if you think about having 3 x's as also meaning that you only have 1 y. Well, how many ways can I make a 4-letter sequence if there's only 1 y? I can put the y right here, or in the second place, or the third spot, or the fourth place. 1, 2, 3, 4 different places. So there are 4 possible 4-letter sequences that have 1 y, or 3 x's. Number 10. Expand the expression x plus y to the 4th power. The work is started below. Continue the expansion, but do not use exponents or combine like terms. As you do this, think about how it is related to permutations. I show you here that x plus y to the 4th power is x plus y to the 3rd power multiplied by another x plus y. And x plus y to the 3rd power is expanded here, as we did earlier, and we are multiplying by another x plus y. So this x will be multiplied by all of these 8 terms, and this y will also be multiplied by each of these 8 terms as well. Here are all of the terms that I get when I distribute the x plus y. The terms in red are what I get when I distribute the x to each of these terms, and then when I distribute the y, I have written that in blue. Number 11. Use your work in the previous scenario to fill in the missing coefficients below. X plus y to the 4th is equal to, and do you see I have here 5 blanks, and there are different terms. If I were to combine these into a term using exponents, it would be 4x's multiplied together, which is x to the 4th. And there is only one term that has 4x's, so there is only one term that is x to the 4th. X cubed y means there are 3 x's. There are 3 terms that have 3 x's and 1 y, and that means that there are also 3 terms that have 1 y and 3 x's. I'll underline those in a different color. 1, 2, 3, and 4. There are 4 terms that have 3 y's. How many terms could be written as x squared y squared? Well, let's count up how many have 2 x's and 2 y's. 1, 2, 3, 4, 5, and 6. There are 6 of those terms. And finally, at the end here, there's only one term that has 4 y's, so its coefficient would be 1 y to the 4th. If you raise this binomial to the 4th power and combine like terms, you would get the following polynomial. In the previous scenario, I asked you to think about how this is related to permutations, placing letters like this. It's actually a combination, which is derived from permutations. The reason this is a combination is because this x being here, or here, or here, doesn't really matter. What matters is that there are 4 x's here. This is 3 x's with the 4th letter being a y. It doesn't matter if I put this x here or here. It's still 3 x's and 1 y, and y is in the 4th position. Because the order in which you place these x's in this 4-letter sequence does not matter, you can refer to this as a combination, not a permutation. And as we saw in the previous scenario, you can use a combination of 4c3 to calculate how many different 4-letter arrangements you can make that have 3 letters that are the same. That is 4c3. Number 12. Before you combine like terms, how many terms are in each expansion below? Do you notice a pattern in the number of terms in each expansion? Part A is x plus y to the 1st power, and that is x plus y, so there are 2 terms. In part B, x plus y squared is xx plus xy plus yx plus yy. That's 4 terms before you combine like terms. X plus y to the 3rd, you saw earlier, has 8 terms, and x plus y to the 4th has 2 sets of 8 terms, which is 16 terms. Now look at these numbers, and you can see that there is a pattern. 2 is 2 to the 1st power, 4 is 2 to the 2nd power, 8 is 2 to the 3rd, and 16 is 2 to the 4th power. When you raise this binomial to a given exponent, the number of terms in that expansion will be equal to 2 raised to the exponent that you are raising that binomial to. So 2 to the fourth, 2 to the third, and so on. Number 13, consider the expansion of x plus y to the fifth power. Part A, before you combine like terms, how many terms are there? X plus y to the fifth power will have 2 to the fifth terms, and that is 32. Part B, how many ways can you create the term x to the third, y to the second? This can be stated another way. Each term has 5 letters. How many ways can you place 3 x's? Each term has 5 letters, and you want 3 of those letters to be x. You can calculate this by finding the combination of 5c3. That's 5 factorial over the difference between 5 and 3 factorial, which is 2 factorial, multiplied by 3 factorial. If I write out 5 factorial, I can write it as 5 times 4 times 3 factorial, and now the 3 factorial in the denominator will cancel out with the 1 in the numerator. 2 factorial is 2 times 1, so I get 5 times 4 over 2 times 1, or 20 over 2, which is 10. There are 10 terms that have 3 x's, so if you combine like terms, your x cubed y squared term would have a coefficient of 10. 14. Fill in the missing coefficients. Part A, x plus y to the fifth. There's an x to the fifth term, a term with 4 x's and 1 y, 3 x's and 2 y's, and then the reverse of these, 2 x's and 3 y's, and then only 1 x and 4 y's, and finally all y's. Let's start with this term. There are 5 x's, so the number of ways you can create that term is 5c5, and 5c5 is just 1. This term has 4 x's, so out of the 5 letters we want to choose 4 x's. That's 5c4, and 5c4 you can calculate on your own is equal to 5. The coefficient here would be how many ways can you pull 3 x's for those 5 letters? That would be 5c3, and you know that 5c3 is equal to 10. When we get to the coefficient of this term, we already know what it must be because we've answered that question when we ask ourselves how many ways we can have 3 x's in a 5-letter term. When you have 3 x's, that means you have 2 y's. So if you have 3 of one thing, then you have 2 of the other thing. And that's what this is, 3 of one thing and 2 of the other thing. There are 10 ways you can arrange that. You could look at the x and say, how many ways can I place 2 x's? So I could calculate that by doing 5c2, but that is the same as 5c3. It has the same numerical value. So we see a coefficient of 10 again. Both of these terms have the same coefficient. This term is 1x and 4 y's. This term is 4 x's and 1 y. 4 of one thing and 1 of the other. 4 of one thing and 1 of the other again. So this coefficient is also the same as this one. We could calculate it from the perspective of x and say that's 5c1 because we have 1x. But it turns out that 5c1 and 5c4 are both just equal to 5. And finally, if we want to know the coefficient of y to the fifth, that's all letters are the same. And we already know that if all the letters are the same, there's one way to do that. So since there's one option for the x to the fifth term, there's also one option for the y to the fifth term. If we look at it from the perspective of choosing x's, then it's 5c0 because we are choosing no x's in our 5-letter term. Now we can look at part B, x plus y to the sixth power. There will be a term with 6 x's, only x's, and there will also be a term with 6 y's, only 6 y's. If we think about this term as picking a certain number of x's, then we have 6 to choose from, and we want to select 6. Or the last term would be 6, choose 0. Either way, both of them has a numerical value of 1. This next term has 5 x's and 1 y, but that's the same number of ways as having 5 y's and 1 x. We can find the coefficient by calculating 6, choose 5 x's, or 6, choose only 1 x. Both of those are equal to 6. If I want 4 x's, then I can find that by calculating 6, choose 4. But having 4 x's is also going to be the same as just having 2 x's, because in this case you have 4 y's. So we can find the coefficient of this term by looking at the fact that there are 2 x's and calculating 6, choose 2. 6 choose 4 is 15, and 6 choose 2 is also 15. And finally, this middle term. If we have 6 letters, how many ways can we create a term that only has 3 x's? That would be 6, choose 3. And 6 choose 3 is 20. 15. What is the coefficient of the x to the fourth y to the third term in the expansion of x plus y to the seventh power? Each of the terms in this expansion will contain 7 letters. So to find the coefficient of this term, you can think about how many ways you can select 4 x's out of 7 letters in total. You can use the combination 7C4. You can also think about it from the perspective of y. How many ways can you select 3 y's from 7 letters in total? That's 7C3. And it turns out 7C4 and 7C3 are both the same value. You can calculate it by finding 7 factorial and dividing by either 4 factorial times 3 factorial or 3 factorial times 4 factorial. It doesn't really matter which one you choose. 7 factorial is 7 times 6 times 5 times 4 factorial. 3 factorial is 3 times 2 times 1. And then the other 4 factorial can be written. And then we can see these two 4 factorials can cancel out. So we can calculate this by thinking about multiplying these and multiplying these. Although on the bottom I see 3 times 2, that's 6. So the 6 on the top and the 6 on the bottom can cancel out. And that leaves 7 times 5, or 35. So your x to the fourth, y to the third term would have a coefficient of 35. You would write it as 35x to the fourth, y to the third. Number 16, if the expansion of a binomial has an x to the seventh, y to the second term, what is the coefficient of this term? Well, there would be 7 x's and 2 y's. That's a total of 9 letters. So I know it's going to be a combination with 9 and then choosing a certain amount of letters of one type. I can either look at it from the perspective of x and say it's 9, choose 7 x's, or I can look at it from the perspective of y and say it's 9, choose 2 y's. Both of those are the same. I can calculate it by doing 9 factorial over 2 factorial 7 factorial, or 7 factorial 2 factorial. 9 factorial is 9 times 8 times 7 factorial, and then the 7 factorial in the denominator will cancel out with the 1 in the numerator. 2 factorial is 2 times 1, and 8 and 2 can be simplified. 8 divided by 2 is 4. That leaves 9 times 4 in the numerator, which is 36. So the coefficient of the x to the seventh y squared term would be 36. 17. What is the fifth term in the expansion of x plus y to the 10th power? Let's start by writing out the terms in this expansion. The first term would be all x's, 10 x's. So the first term would be something x to the 10th. And then the next term would be only 9 x's and 1 y. And then 8 x's and 2 y's, 7 x's and 3 y's, and then 6 x's and 4 y's, and so on. But I can see here now 1, 2, 3, 4, 5 terms. The fifth term is x to the sixth, y to the fourth. So to find out the coefficient of this term, I can think about from 10 letters in total, how many ways can I select 6 x's, or how many ways can I select 4 y's? I can calculate that as 10c6, but that's also the same as 10c4. To compute that, I can write 10 factorial over 6 factorial, 4 factorial, and 10 factorial can be written out as 10 times 9 times 8, 7, and then 6 factorial over 6 factorial times 4, 3, 2, and 1 all multiplied together. The 6 factorial in the denominator and the 6 factorial in the numerator can be canceled out, and then 4 times 2 is 8, so those cancel out. 3 divides evenly into 9 3 times, so I'm left with 10 times 3 times 7. 3 times 7 is 21, and 21 times 10 is 210. So this is equal to 210. So the fifth term would be 210 x to the sixth, y to the fourth. You can see that number 18 follows number 17 in this sequence, but I'm going to stop this screencast here and then pick up with number 18 in the next screencast. I'll call that part 2.